Welcome back everyone. So, we are studying NPTEL course Topological Phases of Matter, in which we learned how generic band structure leads to band inversion and gauge obstruction, and how those things are related to having two charts or two connections. One can have more than two connections, but we mainly focus on two that covers the Brillouin zone, and this is how we get a non-trivial topology. And from this week, because we will take many Hamiltonians and we will rebuild those concepts of winding number and Chern number, and right now I will focus mainly on 2 dimensions and 3 dimension, 1 dimension and 2 dimension, and we will use all these concepts and we will talk about model Hamiltonians to understand in real materials how non-trivial topology arises, and then we will also take various popular Hamiltonian and also some material perspective before we move on to symmetry and 3D and other set of topology. Okay. So, this is the content of this chapter. So, we will again start with a generic 2D Hamiltonian and revise the concept of band inversion and band degeneracy, and how band inversion happens across a band degeneracy, again in generic dimension. Then we will move on to 1 dimension. Again we will start with the generic concept of winding number, then we will talk about a popular model called Schrieffer-Heeger model. Okay. And then we will move on to 2 dimension, in which again we will come back to the band degeneracy in 1 dimension, in which the band degeneracy can happen in a single point or even in a single point in a 2 dimension, which we will call Dirac-Cohn, and we will generalize this to little bit to 3 dimension, just to give a primer of how things sort of easily extend to 3 dimension, but we will look at the 3 dimension separately. And also when the band degeneracy happens in a contour of lines in 2 dimension or maybe 3 dimension also a little bit, and also nodal loop, again the band degeneracy is happening in a contour. And then we will move from the semi-metals to Chern insulators. Again we will talk about band inversions across these band degeneracies from trivial to non-trivial, and we will take a toy model, Rice-Miller model. Then we will take more realistic models called graphene, and which has a Dirac-Cohn. Then with graphene, which we want to open a gap by lifting some degeneracy around the Dirac-Cohn, but now we want to do without any magnetic field, with some synthetic gauge field to get a Chern insulator, which will have TKNN like invariant, but without magnetic field. Okay. Then we will come back to this band degenerate point in a little bit again for 2D, but move on to 3D, and also talk about various semi-metals and their materials and the corresponding models. Okay. Finally, we move to superconductivity. So, I will give a quick primer about the mean field theory of superconductivity for those who are not familiar with it, but otherwise also I would encourage you to go back and brush off your concept of superconductivity. And one more concept I will talk about that you need to brush up is the tight banding model. Then we will talk about something called a key-type model. So, there is a spelling mistake. So, it is K-I, key-type p wave superconductivity and the concept of topological superconductivity. Then we will talk about a new type of fermions which are not electrons, but a fractionalization of electron called Majorana fermions. Okay. So, Brasov tight binding model and basics of superconductivity. I think a book like Michael Tinkham is good enough for the basics of superconductivity. I mean, if you do not get time, do not worry, I will do the essential revisions of the basics and also the tight binding. We talked about it little bit when we introduced TK and N invariant and also second quantization, and we will go slightly deeper. Okay. So, the first one is generic 2 by 2 Hamiltonian. Okay. So, when we say 2 by 2, we mean 2 dimensional Hilbert space, and there can be many degrees of freedom corresponding giving rise to 2 by 2 Hamiltonian, and the popular ones are of course 2 orbitals, maybe 2 sublattice such as in honeycomb lattice, which are made of a unit cell in which one needs a minimum of 2 atom or 2 sublattices, but 2 sublattice which can be of the same atom also. Spin half, although we will talk about spin half later, because to deal with spin one needs to introduce carefully the spinor and time reversal symmetry and so on, and that is pretty much. There are some low energy model in momentum space on graphene in which one would get valley, and when it comes to graphene I will introduce you. But right now these are not a proper basis for real space, but this is more of a field theory like picture of momentum space Hamiltonian, valley, degrees of freedom. Okay. So, let us just call them as A and B or 1 and 2, which will cover all any of them, most likely not here, but to some essential physics it will be very similar, except some finite changes that we will do later. There are things like chiral degrees of freedom and all, which also arises in some field theory way of looking at the momentum space Hamiltonian around some k point, and we will also skip those. It can also have chiral degrees of freedom, but our essential things are these 3, which will denote either A, B or 1, 2. So, we will have some spinor which is psi, or maybe we will call it phi A, phi B or phi 1, phi 2. Sometimes also phi up, phi down, in which it would mean either the real spin or some pseudo spin. I will try to avoid this for the time being. Okay. So, if that is the case, then a generic 2/2 Hamiltonian then can be written in terms of this dispersion. So, this is the dispersion that arises for hopping between all the same orbital 1 to 1 on site term as well as nearest neighbor, next nearest neighbor and so on, and this will be 2 2, which will be again be the same thing between hopping from orbital 2 to orbital 2, which can have the on site energy which may differ from the orbital for 1 and nearest neighbor and next nearest neighbor, and this is 1 2, which is the hopping between orbital 1 and 2, and this is going to be the complex conjugate due to hermeticity. Okay. So, typically, and for different lattice things will change, but let us just assume some square lattice. Typically, this will look like minus 2 t cos kx a plus cos kx maybe even b kx or ky. You can even have higher dimension and so on, and minus the chemical potential. So, 2 2 will again be maybe minus 2 t, let me put t 2 t 1, again it will be same or it can also be different. Minus mu, the same chemical potential which is a entire shift which comes from adding the number of adding a particle to the system, and that particle can be added to either any of them or in some superposition state. So, it is just a constant term. But what sometimes happen is that there can be some on-site energy difference between, because of crystal field splitting and many other reasons, you can have some on-site energy difference between two orbitals. Okay. So, that is why one would put a delta term. And same thing, maybe t prime, which can be e to the power I k x a plus minus e to the power minus plus k y b plus minus. So, I am not writing in details for a specific reason, because these are slightly trickier term which we will be interested in, and this sort of term makes quite a bit of difference in making a theory topologically invariant. Okay. So, this sort of generic cosine term and all are not so much of interest. So, we need some special treatment of the lattice. Okay. So, we will talk about this. So, this is a term, then we can write it as in the D vector form that we talked about, d1 sigma 1 plus d2 sigma 2 plus d3 sigma 3. So, d0 is the on-site energy term and all of them are k dependent. Okay. In whatever the dimension. So, d0 is the overall shift. So, in this particular case it will come as some 2 t1 plus t2, or rather let me do it this way. Epsilon 1 1 plus epsilon 2 2 divided by 2, and d3 is the difference between, is going to be the difference between this term and this term, and that is going to make a lot of difference, which we will identify to call it as Dirac mass. So, this is going to open a gap and we will see how. Okay, so, D1 to D1 will be the real part of the on-site hopping and D2 is going to be imaginary part with a minus sign of the off diagonal term. Okay. These terms of diagonal terms, real part and imaginary part will go into D1 and D2. Okay. And we have studied this generic Hamiltonian without specifying the interpretation earlier. So, we have also studied that the energy eigenvalues will be, and we call it plus minus d0 plus minus d, where d is d1 square plus d2 square plus d3 square. Okay. And we also saw that u plus is going to be d minus d3 d3 plus d d1 minus I d2 u minus, let me write it this way, different books and notes will sometimes choose different overall gauge to write these things in a slightly different way. Okay. But essentially all of them will give the gauge invariant quantities to be the same. Okay. And so, let me give you one more interpretation. So, what these terms are? Okay. So, what these terms are nothing but, so let me call it, okay, let me call it I guess u plus or maybe call it alpha, okay, and beta, so plus and let me call it alpha minus beta minus. Okay. So, what these eigenvectors are? They are nothing but these eigenvectors are nothing but the coefficient of how these energy eigenvalues are expanded in the orbital basis. Okay. So, they are nothing but the functions, and this is something that we often and which what we chose phi 1, phi 2 and here alpha minus phi 1 plus beta minus phi 2. Do not worry about the normalization and all, and they are appropriately normalized. The point I am making is that we learned one thing, that we have some state and then you have some frame and then you have the coefficients, and when we are doing a covariant derivative of a fiber, that means in this case on an eigenstate. So, we have a covariant derivative of the coefficient and the frame, and how the frame changes, which means how the orbitals are being rotated as we move on the manifold, will give rise to the connection on the base manifold, and whereas the covariant derivative on the coefficient will just give you the directional derivative. Okay. And then if you combine the directional derivative and the connection together, then we get something called covariant derivative. Okay, that just takes care of how the basis has rotated. Okay. So, and this is what this guy says. The eigenvectors are nothing but the coefficient of connecting between, and as you know that these two eigenvector form a unit vector form a unitary matrix which rotates from phi 1 phi 2 from the orbital basis to the energy eigenbasis. Okay. So, it is nothing but how the unitary matrix sort of changing is changing as we go in different parts of the manifold, is what is captured here. So, let us take special case 1D, and when you said 1D we just have k, let us say kx equal to k, that is the special one dimensions we are talking about. And in this case also we will set D3 to be 0, and again for simplicity. Okay. Having D3 makes things complicated and also makes few things intuitively physically different, and we will talk about that. Right now we set that. So, we just have D1 which we write as D cos theta phi, let me put it phi, D2 equal to D sin phi. So, the eigenvectors becomes okay. And we have already talked about all this. So, let me just remind you k plus minus minus pi to pi. So, we have some Brillouin zone in 1D going from minus pi to pi, and I will set a to be 1. At whatever the phi we choose, or because phi itself is a phase, the global phase to the wave function. So, whatever the value we had here, it does not matter, we can always add something, some constant phase to the wave function, but it is the difference, how much the phase has changed as you go from minus pi to pi, in which the wave function is supposed to come back, and it is the difference that measures the Berry phase. Okay. And the winding number is just divided by pi, so that we can get an integer value. And so, what we are going is, we are going from minus pi to pi k space to D1 D2 space. So, there are two cases, one is when it happens somewhere here, the loop as we go from here to there. So, this is a trivial case, with gamma equal to 0, and the non-trivial case would be as we go again the same thing, but now the parameters are different in such a way that we go through this point, and then the phi minus pi to phi plus equal to 2 pi, because we are sort of wrapping around the center. Now, let us take an example. And there is also a review article. So, PRL means Physical Review Letters. These are the APS journal and Review of Modern Physics. Both are from APS. Okay, it is also called SSH model. So, the model was developed to understand some unusual solitone modes, localized solitone modes in a polyacetylene CHN 1D chain, in which it is sort of drawn differently in different books, but essentially you just have copper carbon with two different bonds, between the nearest neighbors. Okay. As you know that these are 3 hybridization phase. So, you will have 3 bonds, and so 3 bonds with 2 nearest neighbor can be satisfied in this way. Okay. So, now from solid state perspective, this atom and this atom are different because their environments are different. So, we cannot draw a unit cell with 1 carbon atom and 1 hydrogen atom. We need at least 2 of them, right, and then it can be repeated. And this carbon atom we call A and this carbon atom we call B. So, we now have 2 sublattices or bases, and carbon A, carbon B per unit cell. So, this is 1D. Okay. And now, from tight binding perspective, so the hopping from A to B, let us call it T, will be different from hopping from A to B, but in the neighboring unit cell. Let us call it T prime. Okay. So, in some books and all they will call U or V or sometimes called V and W. Okay. So, these are different notations, the standard popular notations people use, and we will stick to T and T prime. And generally T and T prime are not equal. If they are equal, then you do not need 2 sublattice, and we will see the consequence of that. But when T and T prime are not equal, and whether T is greater than T prime or T is less than T prime, this is where the topological phase transitions will happen. So, the Hamiltonian will be T C A dagger within the unit cell I, but between different sublattice, minus T prime, and this notation means nearest neighbor. So, there is no two summation of I and j sites. So, this is my I and this is my I minus 1 and this unit cell is I plus 1. Okay. So, j is not a different index once you put this angular bracket. J is just means that j is I plus 1 or j is I minus 1. So, nearest neighbor. Okay. Then we will have C A, C J B, and we can have chemical potential and let me put I alpha and alpha corresponds to A and B. One can also put on-site energy difference between the two sublattice, which will lead to a term called D3, but right now we are not interested. In fact, we can also set this to be 0, as we know that chemical potential is nothing but a shift to the energy spectrum. And then one can also put higher order hopping from here A to this A site and B to B side and so on, and A to A site. That will give rise to more complicated band structure, but essentially the topological phases will remain same. Then if we Fourier transform okay, and alpha would correspond to A and B, and we will get a band structure that will be, let me write it in the matrix form. Okay. So, let me define state C K A C K B, and the Hamiltonian then will be 0 epsilon k star 0, because we set the chemical potential to be 0, and epsilon k is going to be minus T plus T prime e to the power minus I k a, because here we will get a e to the power minus I k, here because within the, okay, and here we are in the same unit cell. So, you do not get any block phase, and here you get a block phase. Often we write it as real and imaginary part. So, T plus T prime cosine k, we said A to be 1 plus I T prime sine k, which means we identify D1 equal to T plus T prime. So, this minus sign is a convention, one does not require a minus sign in general, and T2 is minus T prime sine k, and the eigenvalues and eigenvector will remain the same, and okay. All right. So, So, now comes the interesting part. So, our strategy is to go from minus pi in k space to pi, right, and correspondingly we want to see what loops we form, and that would lead to what sort of band structure. So, one thing we learn that if it forms a loop that does not wrap the d equal to 0 region, which means d1 equal to 0 and d2 equal to 0, then we will have a trivial topology. So, the essential condition we already find out that d1 and d2 both. So, we should have a parameter space in which d1 and d2 must change sign, so that as we go along from minus pi to pi, we at least wrap the d equal to 0 region. And to wrap a d equal to 0 region, both d1 has to change sign and d2 has to change sign. Okay. So, for non-trivial topology, d1 and d2 both have to change sign within the Brillouin zone. So, d2 naturally changes sign, d2 goes to 0 at k equal to 0 and plus minus pi. So, d2 is already going to 0 here, here and here. Okay. Now, the question is, will d1 go to 0, and that will go to 0 depends on this condition. Tells us that cosine k equal to minus t by t prime, and cosine k varies from minus 1 to plus 1, which means t1 by t2 t1 by t prime and mod has to be less than equal to 1, and this is the important parameter space in which we will be able to wrap around this, and that will give you a band inversion. Okay. So, now let us draw this phase diagram t by t1 t prime. So, the essential points are 0, minus 1, plus 1, A, B, C, D, E, F, G. These are the A, B, C. Representative point where we expect something different to happen. Anywhere in between minus 1 to 0, things will be similar. Things means topology. So, So, all right. So, now we have two things to draw. So, A t by t prime is less than minus 1. So, in this case d1 does not change sign. So, you will have a loop that will go like this somewhere, right, it does not change sign. D1 changes sign, but D2 does not change sign. D1 always change sign. So, it will change sign, it will go to 0 at here and here. So, from you start from minus pi, go to 0, then you go to plus pi. Okay, so, you close a loop, but D2 does not change sign because of this region. So, in this case the band structure will look like E minus, this is E plus. So, now what happens when we are at T1 T2 equal to minus 1. So, in this case cosine k goes to plus minus 1. Right. Okay, I am drawing it pi by 2. Right. So, it will go to 0. So, where pi by 2, I am making a one mistake. Okay. So, what will happen is that I think this explanation. So, what will happen is that you will or get a Dirac cone where both D1 and D2 goes to 0, okay, and right. Okay, yeah, now I understand. So, what will happen is that when T1 equal to minus T2, you will see here D1 vanishes at all values of k, right. D1 vanishes at all values of k, and D2 always vanishes at k equal to 0 and pi and minus pi. So, that means D1 and D2 both are vanishing at these points. Which is minus pi, 0 and pi. So, this is a So this degenerate point are kind of your Dirac point. Okay, we will come back to this degeneracy. So rather I would also then, although this is a cartoon, but just to be a little more, so we will have some sort of a band that should look like this. You can actually plot it, it is fun to plot. Okay. So around this point, these two guy will start coming in and closing the gap. So now let us take the third example. Which is the interesting one, C, which is T by T2 is less than minus 1, less than minus 1, not equal to. Okay. So now we see that D1 always goes to 0 at the three points, but now D2 will also go to 0 at some point. Right. At some point, depends on the values of this, but not at those high symmetry points. It will go to 0 somewhere, and which means if you draw the loop, it will wrap it, and if you draw the band structure, you will see that let us say here it is red, and let us say the band inversion is happening, that you can figure out from here, from the values of T and T prime you can find out where this guy is going to 0. Okay. I mean where this guy is going to 0, and these two are different. So you will find that that is, let us say that is the point at some k star minus k star So, you will see the bands will have this change of the curvature. Band will remain band, it will still remain E minus and E plus, but then if you look into the weight, which are nothing but these weights, right. Here these weights, and here D2 equal to D3 equal to 0. So, these are nothing but the weight that we have right here. These are the values. If you see that, it will actually make the eigenvector switches from alpha to beta within the given band, and then beta to alpha, okay, and that is consistent with this. Okay. So, now you know a real Hamiltonian in which a band inversion happens, and we did show that this will lead to a winding number of 1, and then that we will again show it in the next class. Okay. With that, thank you for your attention, and I will see you in next class.